hypothesis tests, as we know, are sort of like the foundation of statistics. Like if you want to know like how frequently something happens, or if you want to predict something, you need a hypothesis beforehand to sort of compare if your answer is right. And then confidence intervals help you a lot with assessing your end result. How confident are you that your hypothesis was correct or incorrect? And then how do we calculate that if we're using multiple regression? So again, building off of simple linear regression, we're now working on it with multiple regression. And so we specifically want to know the sampling uncertainty in the OLS estimator of the coefficients in multiple regression models. So again, how confident are we that each of these variables we've chosen are impactful on the model? Like how much are they actually benefiting the model? And then, as I think pretty much as usual, the book is using AIR and Stargazer. And then if we want to later, I don't really have a problem opening an R window and running stuff together. And so with the hypothesis tests and confidence intervals for a single coefficient, I feel like we did that. We covered this a bit already, but we've got testing the hypothesis and testing the alternative. I always get kind of confused as to like the default of which is which, but hypothesis usually that there is no effect, and then the alternative is that there is an effect. Even if what you're trying to test is that there is an effect, then like just the math terms for it lay out this way. And so we can compute the standard error, then compute the t-statistic using this fun little equation. And then from there, we can get the p-value. It's one of the things that's nice to know how the math works once, and then from then on, you pretty much will always have the p-value given to you by whatever program you're using. But if we want to reject the hypothesis at, let's say, like a 5% significance level, so if the p-value is less than 0.05, then our t-statistic threshold is if absolute value of t is greater than 1.96. And that's, these values, usually you grab them from a table that is calculated, or if for whatever reason you're taking an exam, they'll usually give you a table of t-scores and z-scores to work with. And then ultimately, it's up to you to figure out which one you want. So anyways, yeah, so like if we jump back over to chapter 6, and we're running our regression with score against size and English on the school's data set, we can check our t-test coefficients with coef test. And this, I believe, just gives you the regular like summary table, but I haven't checked. Or I guess this is part of the regular summary table. And then if we wanted to compute the two-sided p-value by hand, then we can use the coefficients from 2, 3, so that's row 2, column 3, which is our t-value right here. And then we get the absolute value like we saw in the equation up top. And then PT, I'm actually not sure what PT does. It's a new one for me. But if we do 1 minus and then multiply by 2, we do get our p-value, which is the same as we see here. So we're doing good. And then Again, our 95% two-sided confidence interval, it's suggesting that we're 95% confident, there's a 95% probability that whatever value really exists is within this interval. And so hop, skip, and jump. We can take a look again, going back to chapter 6, because in multiple regression. So we now have the confidence intervals for 5% confidence interval. And you're thinking, why is it 2.5 and 97.5? Because if you add 2.5 from here and the missing 2.5 from here, you get 5. And that's because the confidence interval has gaps on either end. Otherwise, your interval would be like, let's say, instead of 1 to 10, it would be 1 to infinity, because you can't be 100% confident of anything. And so now if we wanted to change it to a 90%, then we do level equals 0.9, and we see our 5 to 95. So I guess another way of putting it is, if we want a 90% confidence interval, our upper bound minus our lower bound will be 90%. And the author does note that confint does not use robust standard errors, which, depending on what you're doing, could be a problem. It's just something to be aware of, and then especially like if you're using a bunch of different packages, to sort of dive in and figure out what exactly is going on. And it can be tricky because it's not always well documented what is happening. But thankfully, R is all about open source. So if you like really need to, you can dive into the source code. But I don't always recommend that. It can be confusing. But he does provide a method to compute it here just in case. And so we get the diagonal matrix and take the square root. I'm not really sure why he raised it to the 0.5, but he did. And then we can get the lower and upper bounds by doing the coefficient minus Q norm times the robust standard error. And that gives us the robust 95% confidence intervals. And then we can do the same for 90%. Again, this is 0.975 because we're missing 2.5 on one end, so that the total coverage ends up being 95%. And so then he asks, can the null hypothesis that a change in the student-teacher ratio size has no significant influence on test scores if we control for the percentage of students learning English in the district be rejected at the 10% and 5% level significance? And so he says 0 is not included in the confidence interval for the coefficient on size in either model. So if we look, it goes from negative 1.9 to negative 0.25, which doesn't include 0, and then a slightly smaller range on the 95% confidence interval, which again is expected because a 90% interval would cover less number line space than a 95% would. And if you're rejecting at a lower level or lower confidence level, I guess higher confidence level, then anything at a lower level will also be rejected, again, because it's occupying less space on the number line. Yeah. So then, sorry, let's see. So if we were to add expenditure per pupil, so we've now got this size of the class, the English, which I forget exactly what it's representing, and the expenditure. We can run our coefficient test again, and we see that expenditure now has all of our values, our t values and our p values have changed. All of them have, but the expenditure now has a p-value of 0.014, which is usually a pretty good indicator, but you always want to worry about overfitting. And so if we compute the sample correlation between size and expenditure, looks like they are pretty highly negatively correlated. So there might be a good relationship there. Oh, thank you, Abdu. I just saw the message. PT is probability distribution function for the student's t distribution. Okay, cool. Again, it's one of those things that I've never, oh, it was on the past page. I've never calculated it by hand in R because it's included in pretty much every model summary. So, yeah.
Yeah, just to add something here, the previous.
This one.
Yeah, so it's explaining here that when we introduce the expenditure, we have sort of a imperfect multicollinearity problem.
Oh, okay.
If you go down, yeah, you could see, like here, you.
Oh, there you go.
Yeah, this illustrates the issue of strongly regression. So imperfect multicollinearity, like
yep.
Yeah.
Thank you.
And we notice that once we include expenditure, size doesn't become significant.
Oh, sorry, I totally missed that. Thank you.
Yeah, so yeah.
Okay. Okay. So if we move to joint hypothesis testing using the F statistic, we now have, taking our numbers from before, we now have this new model equation. And so we want to know, can we reject the hypothesis that the coefficient on size and coefficient on expenditure are 0? To figure this out, we resort to joint hypothesis tests, which are something new for me. So this is very exciting. Usually you're just sort of trying to test one thing at a time. And this imposes restrictions on multiple regression coefficients. And so we can calculate homoscedasticity of the F statistic by this equation. So sum of squares residuals restricted from the restricted regression where we impose the whatever restriction we impose. And then SSR unrestricted is from the full model. Q is the number of restrictions under the null, and K is the number of regressors in the unrestricted regression. And of course, R has a nice function for this in the car package. And so we can calculate it just doing linear hypothesis with our model object from LM. And then we're using our test variables here. Our joint hypothesis test, both of the variables go in a vector. And we get our model output, which shows that the F statistic is about 8.01 and the corresponding p-value is 0.0004. Thus, we reject the null hypothesis that both coefficients are 0 at any level of significance, commonly used in practice. That's a good sign, I believe.
That is actually
bad sign.
That is actually about how, because in here, maybe could you scroll up a little bit?
Yeah.
Is because when we use this one, because you already defined these two, as a
Yeah.
kind of, the reason why it says about the joint hypothesis is we actually testing about the two things here, two coefficients, more than two. So in here, restricted model gonna be score equal like only expenditure. Because in here, null hypothesis is the desired both 0, right? So that means in a restricted model, we don't have these two. And then model 2 is the full model, which is the view we have at the top, okay? And then when we summary each model, we can have some statistics result at the bottom. Did you remember when we
Sorry,
run
the restrict
the
that. I'm sorry, the restrict that model. I guess it should be score. It's like English
yeah.
because we are making restriction on the size and expenditure.
Yeah, because in here up to the top, we actually testing about this is the null hypothesis, right? So
Yeah.
if the size and expenditure is 0, means the beta coefficient size is 0, beta expenditure for size is 0, right?
Yeah, no,
So
I get your point.
yeah,
You know, when you're
yeah.
explaining, you write a score is like distributed expenditure. So I was like, it should have been, let's say, English.
What do you mean by that? Like yeah. Because
Yeah,
English score is like this. So in here, model 1 is just only looking at the expenditure, because our null hypothesis is desired 0, right? So we don't have this one for the model 1. In the model 2, we have everything, okay? And then
no. Sorry, maybe you don't get me. So I was like, in model 1, we don't have expenditure, we don't have size. So we are just like score and English, right? Instead of score and expenditure. If I
okay, yeah, score and
yeah, that was the
English,
point
yeah.
I was just trying to make.
Okay, sorry about that. Yeah, that is the score and English. And then when we try to do each model, we actually have a F statistic, right? And then this F statistic is actually difference between these two F statistics. And then why do we have a degree of the freedom of the two? That is because of we have these two as a difference of the degree of difference parameter between the two models, which is the degree of freedom is 2. So when we difference of the F statistic actually providing us about the chi-square for the degree of the freedom at 2. And then when we're looking at the table in the chi-square table, it produced this kind of value. We can calculate that, but it thinks like at the degree of the freedom at 2, we have when we have a F statistic difference value is like this, p value gonna be like this. Actually, there is a manual calculation for this. We already covered this on chapter 2, but we usually don't use that. But how we can interpret this is when degree of the freedom at 2, if we 8.01 has a p-value of this kind of amount, that means actually both coefficients is highly likely to be not to be 0, okay? Because model 2 gonna have a much feasible compared to the model 1, okay? Because both are actually what is called the nested model relationships. Yeah, that's the thing, okay? And then in the when we talk about the chapter 1 about the like a diagnosis of something, that is because of when we actually cover the chapter 5, you will find that there is a kind of a variance and covariance matrix. Actually, in the diagnosis here is the is the what is called the variance, and then the other diagnosis is the covariance here. So when we take this one, is the covariance, so which is the low square. So actually, standard error is the standard deviation of the error. So then that's the reason why we actually power by 0.5, because we have to root them for this to get the standard deviations. That's the reason why that diagnosis actually powered by 0.5, which is the instead of the getting the variance, we have to need to get the standard error, which is the standard deviation of the error, which is the root square for the variation of the errors, the square errors. You know, because we actually cover about in the chapter 5 about the variance and covariance metrics for the residual errors. Did you remember? So those things, due to those metrics, is the 2x2 matrix. And then when we're looking at the diagnosis, it is a variance value in it. So we can only take those variances and then square root them to get the standard error. That is actually usually robust kind of error, standard error. And then that gonna gives us about those a little bit more robust statistics. And then
Oh, sorry, I'm not getting you.
I think you muted yourself by accident.
Yeah, it's like he muted himself. Sorry, Kim. We're not yeah.
Can you hear me now?
Yeah. Now we can hear you.
So which part did you miss about the diagnosis one?
I think so, yeah.
Okay, when we have a diagnosis part, and then we found the square root, like a power by 0.5, right? That is because of we have in the chapter 5, we actually cover the variance and covariance matrices for the residual error. Okay, so in that matrix is actually 2x2 matrix, which include the diagnosis is the variance of the error, and then the other diagnosis is the covariance. So when we take the diagnosis means this, and then actually standard error is the standard deviation of the residual error. So that means we have to square this one to get the STD, which means SE. Do you understand? That's the reason why we actually power by 0.5 in the previous sections. Do you understand? Does that make clear to you?
I
Any
think
questions?
so.
Yeah, because that's the kind of reason. So, and then when actually in the previous sections, actually author talk about there is a kind of a highly negative correlation between the expenditure and size, right? Like when we try to correlation for that, this is like negative 0.6678 or something, right? It says about there might be about the kind of a highly multi-correlated kind of a problem happens here between these two variables, but I'm not sure this is a kind of a problematic because when we try to do the VIF functions for that model, maybe I don't think VIF factor not have like a expenditure, and when we looking at the VIF EXP factor for the size, it does not have a kind of like a VIF value more than 5, I guess. If we have a more than 5 VIF value for these two, that means it might have a multi-correlated problem in it. But the thing is, by looking at this kind of number, when I looking at this kind of number, I don't think there is no kind of multi-corollary factors in here. Authors just try to present some of the example for the multi-corollary, but usually when we say about the multi-corollary problem, maybe when we calculate these correlations, it is much close to the 0.9 or 0.95 or something, okay? If correlation is like this kind of value, in that case, we can suspicious of some kind of a multi-corollary problem by testing the VIF. So that's the thing. So yeah, so let's move on to the yeah.
As always, it takes me, so much, and it just like it blows me away every time. But that's why we do the book club.
Yeah. Sorry, I had a question in the chat. I don't know whether you've seen it.
Why can we testing the coefficients one at a time instead of doing the joint test? Because that is actually because of in the joint analysis, joint hypothesis is because it's not the kind of testing for because in the multi-regression part, we definitely have there is actually internal relationship between the independent variable, right? So if that's the cases, we cannot there is some of the missing point when we testing the coefficients one at a time, okay? Because that is because of there are definitely unexpected relationship among the independent variable. Actually, the regressions model actually focusing on the identifying the relationship between the independent variable and dependent variable, right? But the thing is, that is actually assumes that according to the regression assumptions, actually independent variable is the independently identically distributed, which is the among the independent variable there is each independent variable is exclusive to one another.
But
okay?
Sorry, is that assumption always true?
Yeah, it is assumption of the linear regression.
Yeah, but I'm saying, does it really make sense? Because in most cases the independent variables are the regressors are usually dependent in some way.
What I mean is not talking about the dependent variable and independent variable. I'm talking about the unexpected internal relationship between the independent variable, not the dependent variable. Okay.
Yeah.
We just assume that there is no relationship among the independent variable when we run the regression model, but that is actually not the case. There might be the always unexpected relationship among the independent variable when we're looking at, right?
Yeah.
So that internal unexpected relationship we cannot control in the multiple regressions. Okay, that's the reason why we have to do the joint hypothesis by setting up the two different models and then try to compare the F statistics that actually allows us to remove those kind of internal relationships, because F statistic is about the distribution of the outcome distribution, and then how those two models is fit to each other, right? Yeah, so that's the reason why in the multiple regressions, we actually do the testing the coefficients one at a time, because assuming that if the other two variable is the holding constant, like an average value, we can testing about another T statistic for the maybe expenditure for the T statistic. But F statistic actually allows us about the overall variation of the variation in explaining the outcome between the two models. That actually allows us to remove the unexpected relationship or interactions between the occurring between among the independent variable. That's the
Yeah.
reason why we actually do the joint hypothesis test.
Yeah, that's clear. Thanks.
Yeah, okay. Yeah, let's move on.
Okie dokie. All right. So if we want to check our confidence levels for multiple coefficients, we can create confidence sets.
Mm,
And so it's a combination of coefficients that contain true combination of coefficients, say 95% of cases. And so I thought that this confidence ellipse made it really easy to understand. So if we were to plot a 95% confidence set for size and expenditure, we have this ellipse, but if we take it, and then we can fill it, but if we wanted to compute the robust confidence ellipse and overlay it, we can see
much smaller one.
these, yeah. I believe it's actually bigger, because if
Okay.
this one's
Yeah,
blue,
right,
so that
right.
means the purple, yeah, it looks like it's a little bit
Mhm.
bigger, but I thought it was a
Oh,
really
yeah.
neat way of just sort of like seeing how your confidence changes within sort of like a continuous range across both
Mm,
variables.
mm,
And then like, I guess in theory, you could even add more variables and then you would have sort of like a 3D shape, but
mm,
I don't know if there's a function that lets you do that already,
mm.
or if you'd have to do it yourself. But and here we go. So the robust standard errors are slightly larger,
Yeah, right.
and so it's analogous to the confidence intervals for the individual coefficients. So size is from here to here, and then expenditure is from down here to up here, it looks like.
Mm.
So it's always nice when you can look at it in a picture.
Mm,
So if we have our multiple regression model and we want to choose the variables, there's lots of ways to do it. But usually, at least in economics, the focus is more on causal effect and not necessarily just finding like an arbitrary set of variables that produce good results. Like in economics, it's all about, can we prove that there actually is cause and effect and not just good correlation. And so they suggest, again, thinking about omitted variables as a way to avoid bias by using suitable control variables. And so, yeah, are we leaving anything out that could cause problems, or are we leaving anything out that we should have otherwise? And so for omitted variable bias to arise, we must have two things. At least one of the included regressors must be correlated with the omitted variable. And the omitted variable must be a determinant of the dependent variable y. And so we're back to our test scores with size and English. So we've dropped off the expenditure variable for now. And so if we were examining the causal effect of class size on test score, there might be bias due to omitting outside learning opportunities from our regression, since such a measure could be a determinant of the student's test scores and could also be correlated with regressors already included in the model. And so that's sort of complicated and hard to quantify because you don't like if this is your class and you're examining like their scores, you don't know necessarily how much outside learning they're doing. So if they're nerds in a book club like we are, then you wouldn't necessarily know. And so we can try and find related variables that might sort of indicate the possibility of outside learning. And so they suggest that a student's economic background would be a good one, because if you come from a wealthier family, your family is more likely to be able to afford the outside learning opportunities. And so we can test that sort of with the inverse variable here, which is lunch, which is the percentage of students that qualify for free or subsidized lunch in school. I think, Kunte, you're in the United States, right?
Yes.
And
Right.
Abdu, you're not? Are you both familiar with the free or subsidized lunches in schools in the United States?
No, not familiar.
No. Yeah.
Okay, so there's a federal, I believe it's federal program that essentially anyone who makes under a certain amount of money qualifies for
Hmm.
a subsidized lunch at school. So in the United States, in like elementary, middle, and high school, they have cafeterias, and students can either bring lunch or buy lunch. And so the subsidized students would still have to pay something, but instead of like $3 or $4 or whatever the current prices are, that was, I think, about how much it was when I went to school. It was like $3 or $4 for school lunch. They might pay like 40 or 50 cents. Whereas if you make even less money than that, you would qualify for free lunch.
Hmm.
And that's all of the funding for that comes through either the state or federal government.
Hmm.
And I think a lot of schools, like especially the larger school districts where there are large portions of disadvantaged people, are trying to move towards free lunch for all students, so that any child who needs to eat can eat. Because in a lot of cases, the school lunch is really like it's the single largest meal some children are getting. And in many cases, it's also the only meal that they're getting. And so trying to make it so that everyone has access to lunch. And then some schools also have sort of like a breakfast where it's just like a little carton of milk and like some cereal or something, or maybe a mug. But that's why this might be a good indicator of family wealth, is because you only qualify if your family makes below a certain amount. So the inverse would be if you don't qualify, then your family makes over a certain amount. Yeah.
Yeah. Okay. Yeah. So, yeah, I heard that because one of my research project is homelessness families. So,
yeah.
Actually, for the homelessness families, for children within the homelessness families, they actually have some set of the lunch vouchers or some subsidies to get the free lunch.
Yeah.
And then but in South Korea, we actually middle school, when we go to the middle school and high school students, school always providing the lunch. That is actually included and supported by the government, and then school actually providing the lunch. Maybe you can Google it about the Korean high school lunch.
I've seen it online.
You might be surprised.
Here, let's see. US public
in the Gambia,
lunch.
it's a different story. We used to have it, but it has been abolished because at some point the government could not afford it.
Yeah, so like when I was going to school, like this is what my lunches might have looked like, where it's like a sad looking burger. And like we didn't have pretzels, or like it was just like a weird gross piece of square pizza. And then if we look,
you can try Korean high school school lunch.
Yeah, and I've seen like it.
It is more diverse.
Yeah.
Actually, there is a kind of a YouTube video about the American high school students actually compare the
Yep.
US lunch and Korean lunch. Yeah. Actually, when I went to the school, at that time there is a no free and subsidized lunch at that time. But the thing is, since what I remember is since 1998 or 6, that's what I guess.
Yeah.
Since after that year, Korean government make a decision to every school has their own nutritions, and
Mhm.
then those nutritions and chef, and then those nutrition and chef should be are responsible for preparing those lunches for all school students, which is like a 400
Mhm.
meal for the students during the lunch time.
Yeah. It's
So
I guess one quick last note on at least the free or subsidized lunch in the United States is that the school doesn't know, and so parents have to fill out a form, but a lot of school districts only send out the form in English, and a lot of parents don't speak English or
yeah,
understand,
right.
and
Yeah.
so they don't know that they do qualify.
Yeah,
And
that's
it ends
correct.
up being a sort of a really big problem in some districts.
Yeah, right. Correct. Yeah, especially for the public school in the low income or some kind of a minority communities school. Those are the actually, so there is a families who fathers and mothers cannot speak English at all. So yeah, in that case, recently actually those kind of form gonna be the bilingual. So
Yeah, so like
yeah.
my school district had there's English, and then we had a very large Spanish speaking and Portuguese speaking population.
Yeah,
So
right.
all of our notices came out in 3 languages.
Yeah,
but
correct.
then there's like some other random stuff that would only come out in English or whatever, and it's a whole big mess. But
Yeah.
anyways,
Yeah.
so if we add lunch, then it looks like all of our p-values go down significantly. But there's no large changes in the effective size. And so although the difference in estimated coefficients is not big, it's useful to keep lunch to make the assumption of conditional mean independence more credible. And that's something that my economics professor in college was always really good about sort of reinforcing, was that it doesn't matter how good your model is if it doesn't make sense. And like, even if your model is a little bit worse off for including something, if it makes sense to include it, you should probably include it, because otherwise you would have omitted variable bias.
Do you think in this case it is maybe like the author says, it is okay to include that variable? Maybe. Yeah.
I think for the purposes of illustration, it is. But I wouldn't.
Because I
think
personally,
the conclusion is wrong. So like outside learning opportunities wouldn't necessarily be what's best indicated by students receiving free or reduced lunch. It would be sort of the environment at home, where students on free or reduced lunch might be spending I know in some places you can work like as young as like 14. And so they would be going out and getting a job to help support their family at 14, and not necessarily then they're not able to spend as much time on school. Or maybe they struggle in school and their parents aren't able to help them as much because their parents are working.
Correct. So Actually, we in the previous sections, we already have a more directly measured core expenditure, right?
I believe
So,
that was school expenditure on the student, not
okay.
so
Not
like
the individual students'
yeah,
expenditure. Okay, gotcha. So in this case, lunch is the kind of an indirect indicator about the family income level, right?
yeah, and
Yeah.
that sort of
Oh,
implies like economic
yeah.
opportunity, and
Mm,
some
mm.
states have
Yeah.
they have standardized testing, and when they
Mm,
release the score summary, they'll release it, I think, by school and by grade, and they'll have the breakdown of like how many students scored with each level who get free lunch, how many students scored at each level who get reduced lunch.
mhm,
And so I
mm,
personally, I qualified for free lunch. Like
mm,
growing up, my family was very poor, and but it was kind of like odd because if you look at the breakdown of scores by free lunch, you
mhm,
could tell like who me and like two or three other students were and how we
mhm,
scored, because we were
mhm,
the only students scoring well in
mm,
the free lunch category.
mm. Okay.
And so there's a lot going on to it, and like
Yeah.
with lunch, like I said, it could be that that's that child's only meal. And
Mhm,
so imagine how hard it would be to like focus on your homework and do
mhm,
a good job if you're only getting one, and I showed you the pictures, one subpar meal a day. It's going to
okay.
be hard to succeed.
Yeah, after I hear the what you or your explanation, I think that lunch seems to be pretty good indicator in this
Yeah,
case. But the thing is, when I'm looking at some kind of a statistical perspectives, I'm a kind of a little bit doubtful about all of these kind of a highly high, very high p-values.
yeah,
So those are
I
the should be worthwhile to testing it. But after hearing your explanation about the lunch, that might be possible to do that. Because the
yeah,
reason why I'm asking you about this is the kind of a doubtful is because of the actually this we have to in this case we have to thinking about the is this one is a kind of like a overestimate
yeah,
or just kind of estimate correctly. So we actually compared to the previous model or the other model,
mhm,
these are the all of the very highly significant sign, which means we actually think also testing about the is there any kind of a overestimation kind of problem. I think
yeah.
that is also related to the omitted variable, but yeah, that's
I
the reason why, yeah, statistical perspectives just only including the launch, changing the
yeah,
all of the p-values into the highly significant, less than 0.001 level. That is a kind of like we have to doubtful about the is there any kind of overestimation problem. And then
yeah,
after the testing, then maybe we will say, okay, then launch can be the one indicator to do that. Yeah,
yeah. I think
yeah,
at least from
yeah.
like personal reading, all three of these are like real good indicators.
Mm,
Like
okay.
there's a lot of literature on how, I mean,
Mm,
and it's sort of like what your mental model would expect, where if you increase class size, you're not
mhm,
also increasing the number of teachers.
mhm,
And so each student gets less individual focus. So any student who's struggling is more
mm.
likely to be
Yeah,
sleep,
correct.
miss,
Yeah,
or like,
yeah.
so
Actually, yeah, actually, I one of my project is the actually try to identify the relationship between the nutrition status of the high school students and their physical activity, and then there is a highly relationship between those two. And then
mhm,
another reason why lunch is included as a indirect indicator of the income is because of the in this data, actually, unit of analysis is cool. But the thing is, when we try to looking at this one, maybe if we have a unit of analysis, data set is maybe census tract or maybe school district, you know. In that case, I think we can find a much direct measure like median income, household income of the school district. That's gonna be the more direct one. But in this case, yeah, lunch is a very good indicator because of this one is a unit of analysis, is the individual school. So yeah. Okay. Yeah, let's move on. Yeah.
So we have R squared and R bar squared and what they tell you and what they don't. And so, like as usual, it's how good of a predictor, how much variance do your variables predict out of all variance? And they don't tell you whether an included variable is significant. It doesn't tell you if the regressors are the true cause of the movements in the dependent variable. It doesn't tell you if there's omitted variable bias, and it doesn't tell you if you have chosen the best set of regressors. I think a lot of the times, especially in like undergrad, it can be easy to overfocus on like getting low p-values and high R squared values. But again, sometimes it matters more about what you're modeling rather than like the numeric results. And so if we generate observations for parking lot space using income, size, expenditure with these, I guess, our coefficients, we can plot parking lot space compared to test scores. And then we can regress test scores on parking lot space. And it looks like there is some positive relationship. But really, we just sort of made up this variable that suggests that more parking lot space corresponds to higher test scores. And so that's not really, that's just due to like correlation rather than causation. There's nothing behind there. But if we then we can sort of dive in and do like a little hands-on real quick before we run out of time. So English is the percentage of English learning students, and lunch is the share of students that qualify for a subsidized or free lunch at school. We also have CalWORKs, which is the percentage of students that qualify for the CalWORKs income assistance program. And those students live in families with a total income below the threshold for the subsidized lunch program. So both variables are indicators for the share of economically disadvantaged children, and they are highly correlated, which you would expect because any student who qualifies for CalWORKs would also fulfill the lunch variable, or almost all of them anyways. Sorry, I'm going to scroll. So there's no sort of one way to decide which variable to choose, because you want to only choose one so you don't have multi-collinearity. It will mess up your model. And so I believe we have some scatter plots here of English, lunch, and CalWORKs against score. And then we can also look at the correlation coefficients between each of them, and they're all negative, as I think you might expect. If there's a higher percentage of students learning English, if you give them an exam in English, they're not going to do as well. And so then we have 5 different model equations with each of our three variables. So English, lunch, and CalWORKs. And then it looks like he's just running them all and then listing them out into a table. And he's using Stargazer to do that. And Stargazer is meant for printing model outputs for multiple models in a nice, easy to read format. And so we have the coefficients for each variable, and then I believe also the p-values. Sorry, these aren't the p-values. I'm not sure what these are.
That is the standard
Yeah,
error.
these are the coefficients, and then up top is the p-values, maybe.
No. Top one is the coefficients, and under the parenthesis is the standard error.
Okay, thank you.
Yeah.
Okay.
Actually,
Makes
when
a
you
lot more
go up,
sense.
when you go up to the top a little bit, the function R functions.
Yeah.
Yeah, in that year, you will see the option
yeah, it's
for the here like
calculating it. Okay.
SE.
Yeah.
Yeah.
And then
So
the p-values are just denoted by the asterisks. I guess we don't have
yeah.
specific values. Okay.
Yeah, right.
And so this states that score is the dependent variable, and if we consider the 5 models,
Mhm.
I mean, just going, if we go based off of R squared, which we just decided is not necessarily the best
Mhm.
method, then it looks like the model with English and lunch
Mhm.
does it does the same about actually as the one with English, lunch, and CalWorks, which is model 5. But our residual standard error is just a little bit lower.
Mm.
So
Yeah, actually, when we're looking at these tables, the Stargazer table, like a coefficients, the
Mhm.
regression table,
yeah.
we actually when maybe assuming that maybe if I can publish the paper for this, we do not include this one. We
Yeah.
only include these 4 because of the, as you can see here, there is a highly correlation between these 2 values. Actually, this model is not good. So we only include these 4. And then the way we can actually testing these 2 variable is, as you can see here, in the model 3, we include this one here. And then the other one, we include this one in the model 4 to testing what's the relationship for the lunch and score and carry works and score. We really think these 2 are the pretty good indicator of the income we need to test in our research. What you can do is, instead of include both variable into the one model, which is not good due to the multicollinearity problem, we do the 2 separate regression analysis. One is to include only lunch, the other one is include only carry works. Okay, that's the how we can try to do these kind of things actually come from.
And so he has some conclusions here that if we add control variables, it roughly halves the coefficient on size. And the estimate is not sensitive to the set of control variables used. And the conclusion there is that decreasing the student-teacher ratio by 1 unit leads to an estimated average increase in test scores of about 1 point, which again makes sense. You have fewer students, you have more ability for the teacher to focus on things that are confusing.
Actually, what this one says about is when we compare to the model 1 and model maybe 3 and 4 or 5 in, for example, actually the coefficients of the size are gonna be adjusted depending on the control variable. So that means in the regression coefficients of the size in the model 1 is a kind of like overestimated, you know, because as the control variable are added to the model, actually coefficient, regression coefficient of the size is gonna become adjusted depending on the control variable. That's what the model 1 is about. And then model 1 also tells about is regardless of regardless of the model we saw at the top, size is always significant, which means there is a kind of a might be the causal relationship between the size and English score, but we cannot highly that might not be certain, but there might be the potential causal relationship on that, but we are not sure yet because we did not include all the control variable here. So do you understand what I mean?
Yeah.
Yeah.
So if we add more characteristics, it increases our R squared and adjusted R squared. And that's usually a good sign that they are suitable predictors. And the estimated coefficients are consistent with the impressions gained in figure 7.2. I don't want to go find this, but I think he's probably right. And then we also see that the control variables are not statistically significant. So in model 5, that CalWorks is not statistically significant, different from 0 at 5%. And we also see that the effect on the estimate and its standard error of the size coefficient is negligible. And so therefore CalWorks is extra and superfluous since we have lunch, and that's what we had talked about up here. So I think we're pretty much at the end of the chapter. We're out of time, but there are these exercises if we could do on our own, but yeah, that's chapter 7.
Okay, so there is a question about the how large does the observation has to be for the F distribution terms. Approximate chi-square Q is I think that might be about, I would say, at least more than 30 and more than 50, depending on the research context. But usually when you get a sample size more than 50, that might be highly likely to be safe for the F distribution test. But in general, 100 is some kind of a rule of thumb, kind of a threshold for these kind of testing, for making this kind of testing gonna be generalizable. But it actually depends on the research context. But usually, depending on what kind of research you have, maybe sometimes if you don't have too many predictors for the outcome variable, maybe you can use the less than 30, but you have to testing about the sensitivity of the DEM model, which is already covered in the previous chapter. But maybe 50 will be okay, or 100 is the kind of a very safe kind of a threshold, because it actually depending on about how many parameters, like how many variable you want to include in your model. That parameter actually determine about your model sensitivity and then the degree of the freedom. So in that case, depending on your number of parameter in the model, that actually determine about your effect sample size for the testing of all of these tests in the regression model.
Yeah, thanks. It's
yeah, because there is actually term for the effective sample size, but actually most of the effective sample size actually depending about the number of variable or number of parameter you can identify in the model. The more you have too many parameters in your model, like you have 100 variable in your model, you need to get at least more than 100 observations if you wanted to include the 100 variable in your model. Yeah, that's the simple thing.
Yeah, thanks.
Yeah. I think this is it. So thank you very much. And then
Thank you both.
yeah, and then maybe
thanks,
next week I'm gonna cover chapter 8, like the linearity. So okay, so I will see you all next week then.
All right, sounds good.
Yeah.
A quick heads up.
Uh-huh.
My sister is graduating from college on the 20th, so I won't be able to attend. But if you both meet without me, I can watch the video.
No, but
You
you
mean
can-
the 20th, right? So
Yeah, on
next
the
week
20th.
next week you can attend?
Next week I'll be here, and I think we have one more weekend. No, next weekend I'll be here. The weekend after I won't.
Okay. So in that case, maybe we were thinking about the skip that week, maybe.
Yeah, we
I mean,
could just skip
we-
that week because it's only three
Yeah.
of us, so we could just go
Yeah.
along.
Okay.
Yeah, we
Yeah.
could just skip that week. Yeah.
All right.
Okay.
Up to you guys. I don't mind if you do want to meet.
No, it's
No,
okay.
no. I think it's fine. The discussions we have, I think it's good.
Okay.
Yeah.
Sounds
Yeah,
think-
okay. So next week I will cover chapter 8 and then maybe May 20th we can skip the week. So
Yeah.
okay, so I will see you all next week then.
All right.
Yeah.
Thank you.
See you all next week. Thanks. Bye.
Yeah,
Bye-bye.
thanks. Bye bye.
Bye.